Hi everyone, I'm Monica Beckwith, and I'd like to welcome you all to this session. There were about 35 pre-registered for the session, but I have a lot of slides and I want to get started. So I guess I'll apologize to them when they come in. All right. This is something about myself. I'm working as a performance architect at a company called Servergy, and in the past I've worked with many other companies as well. So basically I'm a software engineer that knows how to not fall asleep during those hardware meetings, and I know quite a lot of hardware buzzwords as well. All right, something about my company. We do technology solutions, and our main focus is data security. So there are some of the solutions that we have, and big data for IoT is one of the solutions as well, and I'm going to cover Hadoop as a part of that. A few members of the Servergy team. These guys are the minds behind Servergy. Vihara is the VP of Engineering, and Jack Smith is the VP of Technology. They have helped me a lot with the understanding the fabric needs and the systems and kind of like the hardware aspect of it. And they're not here today. So they're not really helping me here. So as a payback, I mean, thank you. I want to immortalize them here forever. All right. Like I said, I have a lot of slides because the way I wanted to talk about this is anybody who's getting started with Hadoop would get an understanding of it, as well as people who know about it already would learn about our deployment solution. So one thing I want to start with is about what is scaling? Like what does scale up or scale out mean? And then from there I want to go ahead and talk about Hadoop and designing the cluster, what our requirements were, and some noteworthy projects if I get time to get to them. All right. So scale up. I hear a lot of people talking about, scaling with Hadoop, and then they're talking about, in the terms that they're using, they may say scale out, but actually what they mean is scale up. Scale up means vertical scaling. So basically, you have, say for example, you're making a system beefier. You're adding more cores to your system. You're adding more powerful NIC cards to your system. You have hardware accelerators, or you're having this PCI extension slots, and you're having dedicated engines to the extension slots. So you're beefing up your storage as well. So when you have this one system and you're making it beefier, that's called scaling up, right? So what are the pros and cons of scaling up? Your unit gets very expensive, right? Your single system gets really expensive. And usually people do that when you're trying to have a hybrid solution. So what happens when you have a hardware failure? Now you have bigger problems because you're selling this hybrid solution system, and hardware failure could result in bigger problems. What are the pros? You have reduced licensing costs. You don't have thousands of nodes now. You have probably tens or maybe maximum hundreds of nodes now. So you don't have as many licensing nodes, right? And you don't have to man multiple servers. Each node can provide a complete solution, like I said, like you can have a hybrid solution. And so now moving on to scale out. It's basically horizontal scaling. You're adding more servers. You could add commodity servers. What are the cons? Footprint. Yeah, physical footprint is a cons of that, right? You need rack space, you need all these, and also you need fabric. Your network needs to be stronger because the network I/O is going to be could be a bottleneck. Of course, increased licensing cost, right? And then maintenance of each node. When you need to have an upgrade, or anything out, you have to do it for every node on your cluster. And then your overall power requirements, because each system has its own power requirements as well. What are the pros? Each server can have less processing units and less memory needs, so like a commodity hardware. And commodity hardware, the definition has changed over the years too, right? But think of it as cheaper system, right? Again, cheaper, right? It says there. And then great scaling, right? Because you have lesser processing units, and you keep adding these processing units, and usually your processing units and memory is not the bottleneck, it's your network, right? And fault tolerance, because now you have these cheaper systems, you can use them for redundancy, providing high availability, and you can scale out as much as you want. All right, moving on to Hadoop, a quick introduction. What is Hadoop? So it's a distributed cluster. This is the basic definition. It's a distributed cluster. It's flexible, it's scalable. Scalable basically can add new nodes as you need them, right? And then fault tolerant. That's the main thing about Hadoop. It's fault tolerant. You have multiple workers, your data nodes, and you have data redundancy. And you have data loss. You avoid data loss through replication. Then let's talk about data parallelism, right? Again, because you have the data distribution and you have replication, that leads to data parallelism. And then the last one is the aggregate system. Basically, you have an aggregate. It's simple. It's very simple. The aggregation system is very simple. It's like in the reducer class, you have the aggregate package, so you can have max, min, or even the total. So, and you can have your own aggregation systems as well. You can add to that. So, what does scale up and scale out with Hadoop means? Again, scale up is vertical scaling. You add more resources. So you're adding more RAM, your hard drives, to your Hadoop data node. And scale out, on the other hand, is basically adding new data nodes, right? You're adding the entire system, new data nodes to it. Scale up is usually, for us, limited. If you're buying a big iron server, it comes at a larger cost. So Servergy, the cluster that we have, the processor that we went with, it enables us to scale out. There's and I have the system right here, one of these 32-bit systems right here. That's a 32-bit server. It's an appliance right there. So we have, because of the system that we have, it kind of gives us good performance, network I/O performance. I'll talk about all these things later on, and the physical size is amazing as well. All right, moving on to the core components. So Hadoop 1 has HDFS and MapReduce. I'll talk more about them in a brief moment. And Hadoop 2 has HDFS and yarn. So what's HDFS? Hadoop Distributed File System. It's written in Java, and it's written for very large files. I'm not talking about terabytes, I'm talking about petabytes of data. And it's streaming data access. So it's basically high throughput, not really good for low latency. And then think about its simple currency model, right? So you can write once and read often. And the way you write to it, so basically not good for multiple writers. And the way you write to it, you append to the end. So, okay. High fault tolerance and data loss prevention, I'll talk more about that in a moment. Automatic addition and compute and removal of nodes. Okay. All right. So let's move on to the next. This is how a basic architecture for HDFS looks like. You have the master-slave configuration. You have the name node, and then you have data nodes on racks, right? So, what is a name node? It's the manager. So it has file permission. Basically, it has file permissions, modifications, namespace. What you need to know is that this information is stored persistently. So it's on your local drives as namespace image and edit logs. And I've highlighted it here because when you're designing, when you're providing the heap space for the name node, you want to know what its persistent data is, right? You want to know the size of that. So that's why I highlighted it over here, and we'll talk about this later when we're going into design phase. So, and then name node also has the knowledge of the location of all blocks. So basically, it's all the files and all the blocks. And this is not persistent. It is stored in RAM. Okay, again, important to know. And the reason, I mean, you don't need to have, it's not the data itself. It's just the knowledge of the blocks. So, where are the blocks? That's all it is. And whenever you start a node anyway, you have to create it. When you start the name node up, you got to create it anyway. So it doesn't need to be persistent. All right. So I was talking about you have the knowledge is in RAM. It's about all the blocks and all the files. So what could happen if you have very large number of files? You basically my memory could become a limiting factor, right? So what has HDFS done? There's HDFS Federation introduced in Hadoop 2, and what it does, it has multiple name nodes, each serving a portion of your namespace. So what's a namespace volume? It's metadata for the namespace and a block pool, right? So what happens is that these are basically independent name nodes, and failure of one doesn't really affect the other, but the data nodes have to register with these name nodes, all of them, right? So to access the federated cluster, the client side will mount the tables and map file paths to name nodes. So this is documented, and if you want to use the HDFS Federation, feel free to research that more. All right. So again, continuing with the name node. Name node is also responsible for ensuring your fault tolerance and providing protection against data loss. So how does it do that? So you have something called block replication factor, and the default is 3. So if there's a block failure, it will result in replication of the block. It tries to maintain the replication factor, so any block failure will result in replication of it. Now that's about the data node. What about the name node itself? Name node itself, like I said, in the master-slave architecture, there's single name node, and it could become a single point of failure. So usually people say, yeah, I have a secondary name node. But secondary name node is not a backup. Secondary name node only holds a snapshot of the primary name node's directory information, and it regularly syncs up with the primary name node. So it's always lagging. And if something happens, data loss is almost guaranteed. So how do you avoid that? How do you kind of take care of not have any data loss? You have something called having multiple file systems. So your persistent data that I spoke about earlier, that needs to be not only on your local file system, but also on NFS. And the writes are synchronous and atomic. So the way you could do something is that, so say something happens, and by the way, a secondary name node runs on a separate machine. So if something happens, the name node's metadata and files on the NFS are copied over to your secondary name node, and you run your secondary name node as your primary name node. So that kind of ensures that you are protected against data loss. Okay, let's move on to data nodes. The data is stored on the file system of each data node. The contents of the HDFS file is split into blocks. So what is a block? A block is a file for a data node. And then you have periodic sync-ups with the name node to provide information on those blocks. And it also provides heartbeat saying I'm alive, I'm doing good. So that way your data node is working. All right. So moving on to the MapReduce component. It supports multiple languages, and it's basically the programming model and also data processing. So the compute, the brain right now and also generates data. So it's distributed and inherently parallel. The way it works is that these are parallel map tasks, and I'll talk about that in the next few slides. And so inherently parallel. It's fault tolerant. Again, the inherent design is fault tolerant, makes it fault tolerant. And map and reduce are basic. Map is key value paired, and you have a map function and a reduce function for your. It's basically an application. When you're writing your application, you have the map function and the reduce function. So what does a job consist of? A job would have your input data and then the program itself, the application, the MapReduce application, and then a job configuration file that tells what needs to be done. And there are two tasks. You have the map tasks, and then you have the reduce tasks. So how does the architecture look? It's again the master-slave architecture. You have the job tracker, which not only does the resource management, it also manages the jobs themselves. And then you have these task trackers running on the nodes, and they're on their racks, right? One principle is that moving data is very expensive. So what you do is you move your compute to your data. So usually, people run the task tracker on the data nodes, and that is a consideration that we have to keep in mind when we're talking about a unit of work for task tracker as well, and I'll talk about that in a minute. All right. So how does a MapReduce job look like? So you have the input, like I said, and then you have your map tasks, and then there is the brain, the shuffle and sorting, and then there's reduce, which produces its own output. And this is basically a simplified MapReduce job. So what does a job tracker do? It coordinates and schedules. So you're coordinating the tasks, you're scheduling the tasks on the task trackers. And it also keeps a track of the progress, like how far and what happened. And of course, the task trackers send periodic heartbeat back, so you know the task tracker is doing good or not. So the way it works is that if you remember the previous slide, the map task will produce its own output, and it's not really complete, So if something happens during the in progress or when it's completed but it's not gone further out in that stage of the job, it can re-execute it. So you're not worried about the computational loss because you have so many tasks going on that you can have. It's kind of fault tolerant in that sense. So and what happens if a failure happens when there's an in process reduce task? You can re-execute that as well because we haven't yet produced the output. So we haven't stored it in the HDFS or whatever. So we can still do it because it's disposable, so to speak. And the failure detection, like I mentioned, is through heartbeat. It's similar to what I mentioned about in HDFS. All right, what about the task trackers? They run tasks, and there's a unit of work, and basically it's basically a split, which is a fixed size piece of input. So there's one map task for each split. And so I was talking about this, bringing the compute to the data. So when you have this split and you want to work on a data block, so what would be the optimal size? It should be similar to your data block, right? Because usually, if it spans 2 blocks or whatever, it'll be unlikely that your HDFS node will store both the blocks. Will have both the blocks. So it's advisable to keep your split size equal to your block size. And like I have already mentioned the other two, MapReduce produces the intermediate output, it's local storage. Your final output is what your reduce tasks produce, and that goes to HDFS storage. Now, so Hadoop 2 has something called yarn. Basically, you could call it yet another resource negotiator, or you could call it recursively like yarn application resource negotiator. So the issue was found out by Yahoo, I think, and they found that Job Tracker is not scalable beyond 4,000 nodes. Not only that, MapReduce itself is a kind of a rigid design, and so kind of when you hit the limit, they decided to design something called the yarn. And yarn is basically splits away the application management from the resource management. And so now your MapReduce is just another application, and it can run on top of yarn. And this is kind of more simplified way of looking at yarn. Again, so your resource manager is up there, it's kind of master, but there is also a master for each slave. And so you have basically node managers on each slave, and for every application, you have the application manager. For example, if you had a MapReduce application, then you would have an application manager for MapReduce application. So if you had HBase running, so you have an application manager for your HBase. And these node managers are managing the configuration and the execution. All right. So moving on to designing a minimum cluster. So these are the requirements that we at Servergy came up with. And like security is in our tagline too. We are advanced extensible security. Security is very important to us. High availability is very important to us. Not only in software, like even in hardware, like our switches provide high availability as well. So what is high availability? It's kind of like a guarantee of downtime. So it's like the 5 nines of availability. And it handles detection of failure, elimination of single point of failure, and kind of reliable crossover. And so I'll talk about that. I'll talk about security, like I said, and I'll talk about how we scale out with a 10 gig Ethernet. And then we'll talk about Hadoop on VMs. This is a common deployment, and I'll talk about that. And then there's future work, because we have the system that we have, the 64-bit solution that we have, it has SRIO on the chip itself. So we want to use that, and there are multiple researches done, and we're still reading about that. There's another thing that we have. We have an SDN solution, and it'd be awesome to integrate Hadoop with SDN. And there is a scheduler that there was recently a paper published. It's called the BAS scheduler, bandwidth aware scheduling for SDN. So I don't have time to cover that here, but there is a link. So so if you're interested in that, definitely go read the paper. So let's design. So first we want to talk about the memory for name node. So say it's simplistic. You had 100 nodes with about 400 gigs of disk space. So you have about 40,000 gigabytes. Your block replication factor is 3. Your block size default, again, 64 megabytes. So you have about 192, say about 200K blocks now. So even if you had 2 million blocks, you would need about 2 gigs, because the rule of thumb is you want to have about 1,000 MB per million blocks, right? So you're still all right. So what we did is that we went with our 32-bit solution, and we just used about 2.5 gigs or so, and we're doing all right now. All right. So moving on to the high availability requirement. So earlier I spoke about the data loss prevention with not just having the secondary name node, but also being able to use a remote NFS, right? But that does not guarantee high availability. Say if your system was down, you would still, kind of going from a cold start, you would still be looking about 30 minutes, and till a new name node comes back online. So how do we get high availability? In Hadoop 2, they have introduced the concept of high availability, and basically you have one. High availability concept is the same. Now Hadoop 2 supports it. So what's the concept of high availability? You have an active name node or active node, and then you have a standby node, right? And the way Hadoop does it, it shares the edit log. So if you bring up say you didn't have for your running cluster, you bring up a standby node, it'll read your complete edit log and then any new entries to it. And the data nodes now have the responsibility to not only send it to the active name node, but also send the information to the standby name node. And remember, because you know data nodes, the data block information is in RAM, right? So it's the duty of the data nodes to send those reports to both. And then there's a conservative failover as well. So basically, remember, high availability, you have detection, you have what happens if it fails, right? And then you have the failover techniques in there too. So the way Hadoop does it, Hadoop 2 does it, it has failover support by Zookeeper, and so what happens is there's a persistent session maintained in Zookeeper, and if the session is lost, Zookeeper knows that something is not right with you. Another thing, okay, so now we didn't have it, but we have it with Hadoop too, right? Okay, so another thing is the concept of fencing, and the way Hadoop does it, I mean, there are other ways to do it, but the easiest is having an SSH fence, right? So when you have the SSH fence, you can basically SSH into it and kill it. Basically, if you have a problematic active node that you want to kill. Another way of doing it is kind of literally called shoot the other node in the head. And what that means is you have a power distribution unit, and you kind of forcibly kill it. So that way the name node that was not responding doesn't come back online and kind of spoil your copy, right? Because now you've already brought the standby up into active, and you don't want the old active to come back alive. So that's pretty interesting. All right, so moving on to security. So security, the way I've learned about security is they talk in terms of the rings of defense and layers of defense, and these are the layers. And I'm going to talk about what's natively available in Hadoop itself. So what's available for authentication, authorization, accountability, which is audit, and data protection. At Servergy, we talk about data protection, and most places probably talk about data protection for data at rest and data in motion. So I'll talk about that as well. So authentication, who are you, right? So the way Hadoop, in native Hadoop, the most common form is Kerberos, and it establishes, prevents impersonation, and then there's like the host identity and services. So it's in very simplistic form, this is what it is. You have the user to services authentication, basically like MapReduce tasks. They use delegation tokens. And then you have services to services as a service. So for example, your SSL certificates. And then you have services to services as a user, such as proxy user. So this is a simplistic form of authentication. All right. Authorization. What can you do? What is your authority? All right. So basically, again, Hadoop in its native form provides access control list, and you can specify, there's an ACL true parameter you can set, and then you can specify, and it's for MapReduce jobs, it's for Yarn, it's for HBase data. So you have the access control list for all those things. Of course, you have at the very basic, you have file permissions, right? So it's similar to Linux user and group permissions and stuff like that. So now you had the authority. What did you do? So Hadoop has a way of tracking that as well. And you have the audit logs. You enable more information if you want to. You can do that in the configuration. Then you have the history. So the history of all the jobs that are running in your cluster. You have the job track for that. You have history for job tracker. You have history for resource manager. And then you have the job history server as well. So moving on to data protection. Let's talk about data in motion first. So the Kerberos itself has something called the SASL protocol, which is basically Java's simple authentication and security layer. And just by having Kerberos, it gives you the protocol access, and it's as simple as just turning it on to privacy. Basically, in that protocol, you have different levels. And then I think by default, it's the first one, which is just authentication. The second level is integrity. And then the third level is privacy. And basically, so just because you have it available, you get it. And the way what does privacy mean again? It guarantees that the data exchanged between the client and the server, and that's just Kerberos itself, right? That any data exchange between the client and the server will not be readable by a man in the middle. We always talk about the man in the middle. So it's not readable because it's encrypted. So it's simple, something simple like that. But what about the HDFS data? So HDFS data has something called the Data Transfer Protocol. It does not utilize SASL. So guess what? Since you don't have that, you don't have quality of protection, which I was talking about, authentication, integrity, or privacy, the two different levels. So how does Hadoop achieve that? It wraps the DTP with the SASL handshaking. And how do you enable that? You use that setting in HDFS site, and you get the quality of protection. And then you can set, of course, you have set it to privacy already. So you get privacy there. So what about HTTP over SSL? Name node, for example, name node UI and the MapReduce shuffle. You have to enable that by doing that DFS HTTPS enable and set it to true in HDFS site. You can also enable two-way SSL, and then you can do the same thing for MapReduce as well, and that's how you do that there. Now, encryption of data at rest. So that's the work to be done there. So now you have. Right now, you have just using your OS or hardware level encryption like you would do for any other thing. Now, at Servergy, we have the Ceph cluster, basically Ceph file storage cluster. And what we want to do, and there's paper published, and I have links to it later, about how you can replace the HDFS, the file system itself, with Ceph file system. And we're looking into that. So these are the references that I wanted to provide right now, because these are what I use to learn about these things, and there's a final link that talks about the Ceph file storage file system and then Hadoop itself. So that's something very interesting to us at Servergy. Okay, so moving on to the scale out with 10 gig Ethernet. This is CTS 1000 right here. This is its block diagram at very simplistic level again. So we have 2 DIMM slots per controller, and we have those 10 gig right here. And all right, so things of importance are the SAS HBA, then you have the storage, you have external JBoard. And I'm not going to talk more about this. This was just to show. And this is the processor that we're using. It's a Freescale processor, Core IQ processor. And this is our 64000, which is the 64-bit solution. It's a T4240 processor, and then it has the SRIO, like I said, available in the backplane itself. And the block diagram right here. So the T4240 block diagram, we don't have time to cover that, so I'm just going to skip that. So what's future for us? So basically, data traffic on Hadoop especially is a big deal. And for CTS 1000, we have it set up such that we use the 10 gig Ethernet ports. And on the chip itself, we have something called DPAA, which is Data Path Acceleration Architecture. And it allows for line rate traffic. And for our next generation, the 64-bit solution, we also have, like I mentioned, the serial rapid I/O, and there's lots of papers on that as well. And it's basically rapid I/O is basically something that you may be used to, like InfiniBand or something, and it's a low latency, high bandwidth interconnect. We haven't done anything with that yet. It's future work. This is again how it looks right now for us. So we have about 5 on each side. Like you see, this is a 32-bit solution. We have 2 switches, again, for high availability. One is redundant, so active and standby. And that's a simplified solution right there. And for CTS 64000, the 64-bit solution, it's similar, right? High available switches. Future work, like I said, this is what we want to get to. We want to use the SRIO switches, again, redundancy for high availability, and we want to scale, through the backplane switches, and get to something like this. So basically, we'll have about 1,440 cores, all linked to 20 gig of the SRIO that I was talking about, and you have about 4 hops maximum distance between any 2 processors. And then you have redundant paths because we have 16 switches. All right. So designing a minimum cluster, Hadoop on VMs. That's what we have right now. So why do we virtualize? You want to gain elasticity. You can basically quickly grow your cluster, right? And then system utilization. You want to push the maximum utilization out of your cluster, out of your system itself, single system actually. Better security, because you can separate your computation from your data, right? So you provide security. Multi-tenancy, consolidation of multiple clusters, that's multi-tenancy. And of course, ease of deployment. You could just take a single image and clone it and deploy it, right? So what do we have right now? This, in a very simple form, you can run VMs, and the way you will run VMs, because of the bringing your compute to your data node, you want to run your task tracker and your data node on one VM, and kind of keep on doing that on every VM. But does that really, it's not really elastic. It's if you wanted to add a VM, right, for example, you would need new data, right? Because you already have you had pre-configured your cluster already, and new data will be the need for adding a new node, new VM, right? And also, there's not really separation. It didn't give us the security that I was talking about earlier. There's not really separation of computation from data. So a more elastic way would be something like this, where you have a VM running your data node, and then you have your task trackers running. And then this is highly multi-tenant as well, right? Because you get the isolation. Your compute is different than your data, and you have the isolation that we're talking about. And then when you're adding, the elasticity part of it is you can add more task trackers. So what do you have to do here? You have to find a good balance. How many task trackers per data node is what you have to look for? So I don't know. Right now we're working with 3:1, and of course there's more work to be done to find out the optimal solution, but that's what it is right now. So I'm going to talk about a few noteworthy projects. HBase. It's written in Java, and it basically runs on top of HDFS. HDFS provides streaming access. So what if you wanted to do real-time read-write, right, or random? So basically, you can use HBase when you have millions or billions of rows, and data is stored in tables, rows and columns. It's not RDBMS. It's no SQL. It's distributed database, and it helps you with low latency, fast lookup. What about SQL on Hadoop? We have Hive, and now more recently we have Impala. So basically, you have the Hive is Hive QL, and it only uses MapReduce, and it's an analysis of any data stored in the HDFS and compatible file systems. Impala is SQL query engine. No, it doesn't have MapReduce, only daemons and slave nodes, and it's interactive analysis for any data stored in HDFS or HBase. I'm going to talk about Knox Gateway. It's a very upcoming project. It started as a perimeter security, and these are slides that I have gotten from this presentation that was done on at Hadoop Summit, and Larry provided these slides to me. So I have a link to the slide that gives more details on links to the slide share that gives more details on these slides. And I just wanted to mention it very quickly. It exposes REST APIs and HTTP, and basically it has enhanced security, simplified access. And please go ahead and refer to the link that I have earlier, because it talks a lot about all these things in details. I've just captured the slides. I've just copied actually the slides right here, and. Enterprise integration is also a feature. Centralized control, very, very important. Now, for us at Servergy, since we're using Freescale, which is a PowerPC, for a long time we didn't have the C2 compiler, and so we're thankful to OpenJDK PPC export, and they have done a great job, and we use for our 64-bit solution we use the compiler. What else do we do at Servergy? We help Freescale drive the IoT. It's basically a truck, literally a truck, and it has all these solutions, and it's going to be on the road for 2 years. And if you want to find more information on that, you can go to that link, iotfreescale.com. Basically, it's Internet of Tomorrow, and they have cool solutions there. So if you have any questions, please feel free to email us. I had one backup slide that kind of talking about how do you know your cluster. So think about your hardware aspect and your software aspect. So hardware aspect would be power usage. How efficient is your cluster? Space, high density, like for example right here. Cost. Not just the processor, but your SSDs versus HDDs and the NIC cards and everything. Compatibility, device drivers, firmware, OS. And bandwidth, how much bandwidth, memory, and I/O itself. Like I said, like rapid I/O, serial rapid I/O is really low latency, high bandwidth. So what about the software aspect? You don't want, you want to have security as your major thing in now for your cluster. So virus scanning, network monitors, avoiding man-in-the-middle encryptions and stuff like that. So compatibility, again, your solution for your hardware and OS, you should be compatible, right? You can't just have it as a disjoint solution. It has to be compatible with what you are running on and what you're offering. Supportability, again, is very important as well. So that's all I have. Thank you all for listening. And if you have any questions, thank you.